Hello again, this is EEE 41, Lecture 5. For this lecture, we'll discuss band bending, and so our ABDs will not anymore be consisted of plain, flat lines. We'll also see how the voltage and electric fields within our semiconductors are related to how the ABDs are or must be drawn. We'll also discuss diffusion current and combine our results with the drift current. And lastly, we'll introduce in this lecture the handy Einstein relationship equation. Our objective for this lecture is to be able to compute and plot the voltage and electric field from the ABD and vice versa, to be able to draw the ABD of a non-uniformly doped semiconductor in equilibrium. So now we will consider doping concentrations that vary in space throughout the material. And lastly, to compute and plot drift and diffusion currents as a function of position in the material. Okay, potential versus kinetic energy. Voltage is based on potential energy difference across 2 points for a unit charge. Thus, we need to identify the potential energy in energy band diagrams. In a previous lecture, we identified that the kinetic energy for electrons is the difference between the electron energy and the energy level EC. If we denote EREF as a point of zero energy, then the distance between the electron's energy level must be the total energy, or the distance between the electron's energy level and EREF must be the total energy. Thus, knowing the total and kinetic energy, what's left must be the electron's potential energy. Equation-wise, this can be written as the potential energy of the electron is equal to EC minus EREF, again where EREF is some zero potential reference energy level which may be taken at random but must be consistent in the system being considered, much like how we choose ground nodes for our circuits. Thus, since EREF is just some random constant energy level, information on the potential energy in the energy band diagram can be determined only from EC. And take note, like voltage, potential energy is always relative. It won't matter where EREF is, what matters is where EC is relative to where EC is at a different point in the material. If we apply some voltage to a semiconductor material, we are introducing an electric field pointing from the plus side to the minus side of the positive voltage drop across the material. Thus, the electric field must be pointed to the right in the example shown. Also, since we have a uniformly doped semiconductor with uniform resistance, then the voltage must decrease linearly until 0 volts from x is equal to 0 to x is equal to L. The voltage is the potential energy difference per unit charge. We can write that as V is equal to PE over Q and rewrite as PE is equal to Q times V. The charge of an electron is minus Q, while the potential energy is EC minus EREF. We can rewrite this equation as V is equal to 1 over Q times EREF minus EC. Note that the same equation can be obtained for holes. The charge of a hole is positive Q, but with the hole energy increasing as you go down the energy band diagram, the other side will also be negated and will still end up with V is equal to 1 over Q EREF minus EC. We have already established how the voltage in our example should linearly decrease to 0 volts. We also have the equation that relates the voltage to EREF and EC. We can start by isolating EC in the equation since we want to plot the energy band diagram. Here, we get EC is equal to EREF minus QV. Next, we can randomly draw a constant line and call it EREF, and note that the length of the semiconductor is L. Evaluating the equation at x is equal to 0 will give us EC is equal to EREF minus Q times 0.7 volts, or EC is equal to EREF minus 0.7 electron volts. Thus, we must draw EC 0.7 electron volts below EREF. We can then draw EC linearly until it reaches EREF because at x is equal to L, V is equal to 0, and thus EC is equal to EREF minus 0, or EC is equal to EREF. Since we already have a plot for EC, we just draw EV below it by EG. We can also draw EI right at the middle of EC and EV. Note how the plots for the voltage and EC looks like. We note that we can just flip the voltage to plot EC and vice versa. That is, to get the general shape of the other. When drawing the EBD to voltage and a reference voltage is given, for example 0 volts at the far left of the material, then we just proceed with drawing following the shape of a flipped EC, then identify the actual voltage values afterwards. Note, however, that the EBD is in electron volts and not in voltage. In the formula, we can just replace Q as 1 electron and quickly convert to electron volts. That is, for this equation, there is no need to use the value Q is equal to 1.6 times 10 to the minus 19 coulombs. When drawing from voltage to EBD, EV and EI can be drawn relative to EC given that we know EG. This variation of EC, or the EBD as a whole, with position is what we refer to as band bending. From our discussion, it is obvious that if band bending occurs, then some voltage or potential difference must be present inside the semiconductor. From the voltage, we were able to plot the EBD. We can also plot the electric field given the voltage. As explained previously, for a uniformly doped semiconductor with an applied voltage, the electric field is constant. We can use this equation, E is equal to negative del V or minus dV over dx, from EEE 23 to relate the electric field and the voltage. However, we already have an equation relating EC and the voltage. Thus, differentiate the equation for V and substitute in this equation. The derivative of V with respect to x is simply 1 over Q times the derivative of EREF with respect to x minus the derivative of EC with respect to x. However, since EREF must be constant throughout the material, then its derivative must be 0. We then get this equation for the electric field, which tells us that we can plot the electric field directly from the EBD by differentiating EC. This also tells us that if EC is flat or if the energy band diagram is flat, then there is no electric field inside the semiconductor. Note that in this equation, we can just use Q is equal to 1E or 1 electron to cancel the E in electron volts for EC. Or in other words, since EC is in electron volts, differentiating it along X gives us electron volts per centimeter, so we just cancel the E to get volts per centimeter for the electric field. Here, we summarize the important relationships we have just introduced. The voltage, electric field, and the energy band diagram is tightly related to each other. Knowing one out of three gives enough information to determine the remaining two. From the voltage to the energy band diagram, or EC, we can just flip the plots and get the other because of the negative sign in this equation. From the EBD, we can differentiate EC to determine the electric field. However, the reverse cannot be done. Instead, one needs to integrate the electric field to determine EC or the EBD. For voltage and electric field, we can use this equation from EEE 23. We now proceed with determining the drift current through the EBD. The drift current depends on the electric field direction, which can be identified from the slope of EC. In the example shown, since EC is decreasing, then the electric field must be negative or going to the left. Thus, with this electric field direction, the electron in the figure must drift to the right in the opposite direction as the electric field, while the hole must drift to the left in the same direction as the electric field. Thus, we can still use the balls and balloons analogy to visualize the drift in EBD with balls rolling to the right and balloons floating to the left. However, when asked what the direction of the drift current is, then the answer is to the left for both JN drift and JP drift, since current is the flow of positive charges. If electrons drift to the right, then drift current must be to the left. Remember also that drift currents for electrons and holes should always have the same direction. Thus, in this example, JN drift and JP drift must both go to the left since the electric field is going to the left, since Q, mu N, mu P, and P are always positive. We have already discussed the carrier action drift up to the point that we can visualize it in the EBD. In this part, we shift our focus on the second carrier action, diffusion. Again, particles diffuse from regions of higher concentration to regions of lower concentration due to random thermal motion. This is true for both electrons and holes as depicted in the picture. But is this really the result of random motion? Let's visualize diffusion through random thermal motion in this example. will start with 1024, say, electrons in the leftmost bin. Now, due to random thermal motion, each particle has an equal probability of jumping to the left or right bin. Let's say particles move into adjacent bin every tau seconds. After 1 tau, in average, half will go to the right and half will go to the left, but since there is no more compartment to the left, then the other half will just end up in the same bin. After a second tau, particles will go to the left and right, ending up with the distribution shown. Here we can see why we ended up with 256 on the second and third bins while having 512 on the first bin. On the third tau, the distribution will look like this. So here we note that 128 went to the fourth bin, 128 went to the third bin, while 128s went to the second bin and 128s went to the first bin. Or sorry, the purple one is actually equal to 256 each because it came from 512. So we end up with 384. The diffusion process continues, and thus, in effect, diffusion by random thermal motion tends to distribute the particles evenly throughout the material. However, as the carriers are not yet evenly distributed, we can see a net movement of carriers. Okay, so that is how diffusion happens through random thermal motion. Now, how do we quantify the current? Consider the electron and hole concentrations shown as a function of position or space. From the plots, we can say that the derivative of n and p are both positive with respect to x. We will use colors to help us visualize the amount or density of carriers. Since there are more electrons or holes on the right, then electrons and holes will tend to diffuse to the left. However, as current is defined as the flow of positive charges, then the electron diffusion current must be to the right, while the hole diffusion current must be to the left. That is, even if for both cases, the derivative of the carrier concentration is positive, we ended up with different diffusion current directions. We will proceed with using the following equations to quantify the diffusion currents. Note how 1, the expression is dependent on the concentration gradient and not the actual value of carrier concentration. 2, the formula has a negative sign only for hole diffusion current. And 3, we introduce new constants dN and dP, which are diffusion constants or diffusivity for electrons and holes respectively. The units for diffusivity is cm squared per seconds, with Q in coulombs and dP over dx or dN over dx in per cm to the 4, then we'll get current densities in amperes per cm squared. dN and dP are analogous to μn and μp for drift. Now that we have an expression for the diffusion current densities for electrons and holes, we can now formulate the total current density, which includes both drift and diffusion current densities. The total current density can also be decomposed in terms of the electron and hole current densities. The electron current density with both drift and diffusion is shown. The version for holes is shown as well. The equations are the same in form, but have a negative sign again for the diffusion current component for holes. Alternatively, the total current density can be decomposed in terms of drift and diffusion with electron and hole components for each, where J drift is equal to Jn drift plus Jp drift, and J diff is equal to Jn diff plus Jp diff. The total current can then be written as J is equal to J drift plus J diff. We will use the drift and diffusion currents to analyze what happens inside a non-uniformly doped semiconductor under thermal equilibrium. A non-uniformly doped semiconductor is one where the doping concentration varies with position. Thus, the carrier concentrations also vary with position, even under thermal equilibrium. For such a material, the Fermi level EF varies in position relative to the band edges. The Fermi level can also be said to vary relative to EI, as EI is just midway the band edges. However, we mentioned previously that the Fermi level is flat or constant for a material in thermal equilibrium. How then do we proceed with drawing the EBD of a non-uniformly doped semiconductor under thermal equilibrium? Consider an N-type semiconductor whose doping concentration is heavier on the left side and lighter on the right side. The easiest thing we can draw is EF, since the Fermi level must be flat in equilibrium. Next, we can draw EI farther from EF on the left side than on the right side, based on these following equations. After drawing EI, EC and EV can be located using EG. We can then identify diffusion and drift components from the information that we have. As for diffusion, we know that the left side is heavily doped while the right side is lightly doped. And also using the equations above and the figure, we can conclude that electrons must be diffusing to the right. For drift, since electrons can be seen as balls rolling for drift, then electron drift must be to the left. The opposite directions for drift and diffusion help in achieving the equilibrium state where carriers do not have net movement. In equilibrium, there is no net flow of electrons, neither for holes. And if there is, then the material must not be in thermal equilibrium. Thus, Jn, or the current density for electrons, must be 0, and Jp, or the hole current density, must be 0 for a material in thermal equilibrium. For this to happen, the drift and diffusion current components for electrons and holes individually must balance each other to achieve thermal equilibrium. Thus, in our non-uniformly doped semiconductor, a built-in electric field is created and exists such that the drift current component can cancel out the diffusion current component due to the concentration gradient. Written in equation form, Jn can be expanded into Jn drift and Jn diff, and further expanded into Q mu n n e plus Q dn dn over dx and be equated to 0. Also, this means that Jn drift is exactly equal to the negative of Jn diff for the two to cancel out. We can also say that Jp drift is equal to negative Jp diff for holes throughout in a semiconductor in thermal equilibrium. However, please remember that at thermal equilibrium, we say that Jn is equal to 0, and Jp is equal to 0, which makes the total current density equal to 0. However, the drift of electrons do not cancel out the drift of holes. So this is not true. Neither do the diffusion of electrons cancel the diffusion of holes. So this equation right here is not true as well for materials under thermal equilibrium. Again, under equilibrium conditions, Jn is equal to 0 and Jp is equal to 0 must both hold true regardless if the material is intrinsic N-type or P-type. So if we have an N-type semiconductor under thermal equilibrium, Jn is equal to 0 and Jp is equal to 0. If we have a P-type semiconductor under thermal equilibrium, still Jn is equal to 0 and Jp is equal to 0. Note that electron and hole currents can exist regardless if the material is N-type, P-type, or even intrinsic. From this, under thermal equilibrium conditions, we can sum the electron current components to 0 and also sum the hole current components to 0. Using these expressions for N and P and substituting into the current equations, we can come up with these very beautiful equations called the Einstein equation or Einstein relationship. This equation relates the diffusivity and mobility to the thermal energy, or rather the thermal voltage. The book also notes that the equation rhymes well to easily be remembered. So D over mu is equal to KT over Q, and even the reciprocal, mu over D is equal to Q over KT, also rhymes, which is very cool. In this equation, if KT is equal to 0.026 electron volts at room temperature, then we can just use Q is equal to 1 electron volt to cancel with E in the electron volt. Or it is actually easier to consider KT over Q as a whole and remember that its value is 0.026 volts at room temperature. Note that although this expression is derived under thermal equilibrium conditions, this equation can also be used under non-equilibrium conditions. However, the Einstein relationship only applies for non-degenerate semiconductors, like these two equations here, are also usable only for non-degenerate semiconductors. We actually analyzed the non-uniformly doped semiconductor based on the carrier concentration N and P without saying anything specific regarding the doping concentration. Since if the carriers are drifting and diffusing all around, then can we still say that the majority carrier concentration does not go far from the doping concentration? We can use a simplification called the quasi-neutrality approximation. In this, the majority carrier concentration distribution, or as a function of x, does not differ much from the doping concentration, given that the doping concentration only varies gradually with position. In effect, the charge neutrality equation can be said to still hold, but locally, on different regions of the semiconductor. In an N-type semiconductor, where the electron concentration is much more than the hole concentration, then we'll end up with the familiar expression where N is approximately Nd minus Na, albeit a function of position. A further simplification is that when only donors are present, then we end up with N is approximately equal to Nd. The same expressions can be made for holes where P is approximately Na minus Nd as a function of x. For an N-type material in equilibrium, we get this equation for zero electron current. Knowing that the electron concentration is approximately the donor concentration, we can determine the internal electric field by knowing how the doping concentration varies with position. Thus, given Nd of x, we can determine the rest of the carrier concentrations, the electric field, the drift current, the diffusion current, all as a function of position when the material is in thermal equilibrium. To summarize, we can just flip and differentiate the EBD, meaning EC or even EI or EV, to get the general shape of the voltage and the electric field respectively inside our semiconductors. We have also introduced the electron and hole diffusion current density equations that depend on the concentration gradient and a new material property called the diffusivity or diffusion constant. The equations for diffusion currents also differ in sign, unlike in drift currents where there are no negative signs for both JN drift and JP drift. The total current in a semiconductor has 4 components based on drift and diffusion and for electrons and holes. At equilibrium, the currents for electrons and holes individually must be zero. Lastly, the Einstein relationship relates the diffusivity and mobility by the thermal voltage kT over Q. Okay, that's it for lecture 5. Thank you very much.